APIs, you deploy your application to them, and they will host it for you. We do the same thing. You can give your application to us instead, and we will hook it up in a distributed system and make it all play nicely. We can deploy automatically to Amazon EC2 or Eucalyptus, the open source implementation of those APIs, and we use the standard web deployment model. You go to load balancer, route to your application server, and there's a database on the back end. Nothing revolutionary there. As far as this project is concerned, however, we had to modify a number of pieces within AppScale itself. There's a set of command line tools that AppScale uses to start up boxes, get rid of boxes, and so on. And we modified these tools to add what we call placement support. So you could say, make a certain machine take on a certain role in the system. And as far as Neptune was specifically concerned, we want to be able to start up hot spares in the system. We want to start up 16 boxes, leave them open for computation, and then the system will use them as it needs to. Because spawning up these boxes can take 5 minutes, 10 minutes, depending on the size of your boxes. Additionally, we want to be able to say, I've got resources on the west coast of EC2, the east coast of EC2, some local boxes I want to pull into the fray. I want to be able to aggregate all these boxes into a single place and not have to start up multiple app scales and have them talk to each other in some overly complicated fashion. So we have this hybrid cloud support, is what we call this. We also took a special daemon that runs within AppScale called the app controller and modified it through Neptune. This is basically the runtime component that we talked about earlier. It can receive certain messages that the language level will send out and will act accordingly. Because the point of AppScale is to automatically configure and deploy applications, we extend this from just web apps to apps in general. So if you want to run an MPI job, you tell it 8 nodes, and here's what type of hardware you should use. It will go acquire these nodes on your behalf and run your job for you, start up NFS, MPI, whatever it is that you need to do. We also saw that commonly cloud infrastructures will charge you on a per-hour basis, and that tangentially, most code that users were giving us did not run in exact hour increments, or were not aware of this in any particular fashion. And we didn't want to make you, the programmer, have to be aware of this. So we automatically will reuse your virtual machines for you so that you don't have to get billed for the half an hour you spent on some machine. And if you want to run another job for half an hour, you should only have to pay for the 1 hour that it took to get these jobs done, as opposed to 2 hours because you acquired 2 sets of machines. So simple optimization there. We also have the ability to do more intelligent scheduling if you don't know how many nodes your code needs to run optimally. What this means is you can tell us, my code runs on powers of 2 boxes, any number of boxes, 10 boxes. And we will try to add more machines to the computation until we find some sweet spot where you're either not getting any faster or the amount of money you're paying in dollars is not being properly amortized. We can do either or cost or execution time or the weighted average. But we are looking into more interesting algorithms on that. As far as the types of code that we actually run, MPI is the most commonly used one within Neptune. There are a number of different implementations out there, Java, Python, C, C++, and so on. We take the most commonly used one, which is the C, C++ version. Since MPI requires a shared file system, we use NFS, the network file system. We are also looking to support for Lustre, which is supposed to be better performance. As far as the user is concerned, you only tell us how many nodes you want to run your code over, where's your code on your local machine, and where do you want the output. And we'll take care of the rest. IBM has an interesting alternative to MPI. Their train of thought was more that pointers are too complicated for programmers these days. And if it's not Java-like syntax, it's going to be hard to teach people how to use this thing. So they have their language called X10, which is exactly what I said. No pointers, no memory management, they'll take care of all that for you. It compiles to MPI, so we get support for it within Neptune for free. Again, just tell us how many boxes you want to run it over and what your code is, and we got the rest. Also pretty standard is support for Hadoop MapReduce. Google popularized this programming model back in 2004. Obviously, it was around much longer in the functional community in the map and reduce primitives. As far as the Hadoop implementation goes, they have 2 different types of MapReduce. In the standard flavor, you have to give it Java mappers and Java reducers, and it will go make the magic happen. In their less commonly used, but I think it's more interesting, streaming model, you give it mappers and reducers in any language, and specifically any combinations of languages. I can give it some mapper code in Ruby and some reduce function in Python, and it will use standard out and type all of those nicely across multiple machines and marshal when it's needed. We have support for both of them within Neptune. If you're running the regular flavor, you tell us where your Java archive is located. We'll take care of that. In the streaming version, you tell us where your map or code is. A perhaps more interesting use case. We had biological, computational biologists come to us and say, we run these simulations where some chemical processes occur that are basically Monte Carlo processes. We're going to flip a coin and we're going to make some kind of change in the state of our biological computation. And right now we have one machine and we run this code 1,000,000 times so that we can get some kind of statistical accuracy on our method. And we thought, if all these simulations are completely independent of each other, why are you just running on one box for 2 months? Why don't you just get 100 boxes and then just run 100 simulations on each of them? And that's exactly what we did. With our support for their simulations, you just tell us, 1,000,000 simulations, here's where the output should be, and we'll run it for you. We are looking to expand this work. They have said that even requiring us to specify how many nodes they want is one level of abstraction that their users do not care about. They specifically are caring about, I have a deadline, I need to show my boss the results of these simulations by 2 p.m. Monday. And I don't care how many nodes it is, just get it done. Or alternatively, get it done within $10 or $20 of computation and go from there. As far as what the actual code looks like, this is a simpler example of what we typically run. The top half of the screen starts the initial job, and we say, I want to run 1,000,000 simulations in the system. Most of this is standard Ruby, and the second half of the code will actually wait for the output to finish. So that top part is asynchronous, and it just gets the job kicked off. A more realistic use case of this is to put this in a big fat loop. What these biological computational guys want to do is run some number of simulations and then see what the statistical accuracy of the actual code was. And then if you don't have enough accuracy, run another 1,000,000 simulations, or another 50,000, or adaptively change the number of simulations you're running. So in the real case, this is in a big fat loop. But that's just one example of what this looks like. I keep talking about what storage and output looks like, but I don't really specifically say what it is. Here's what it is. Since we're running over the AppScale cloud platform, we can take any of the 9 databases that they support and automatically store to those. We've highlighted 3 here, Cassandra, HBase Hypertable. It's all automatic. You don't have to know what the replication looks like, where the machines are hosted. It's just, here's a piece of data that what we require. We also can store to Amazon's S3, their simple storage service. So you can use any of the tools that are integrated with that, the Firefox plugin and many others, to automatically move your data if you want to show it to your boss later. We also can use anything that's API compliant with that. So you can look at the Walrus implementation and there's a Google Storage implementation, which is the exact same API. We also wanted to be able to say that Neptune is cool for HPC, but it's not constrained to HPC. So to demonstrate this, we use Neptune as a way to scale up AppScale itself. You can say in a Neptune job, give me 2 more load balancers, 3 more application servers, a database node, and it will automatically talk to AppScale and get this done for you. Since we have this hybrid cloud support, we also can say, go to Amazon on the East Coast and give me 3 more database nodes, and go on the West Coast and give me a couple more application servers in a single request. You don't need to know where these machines are located. You just tell us, I have some cloud somewhere, and here's my credit card information. We'll take care of the rest for you. Neptune does not solve all problems. It will not magically make code run fast, etc. And there are a couple classes of problems that we do not solve yet. The first type of class of problem is problems where I need to have the IPs of these machines or some unique identifier hard-coded into my code. The typical use case of this is airline, where the naming is handled at the actual code level itself. We also have an issue taking care of closed source software that needs to run within these virtual machines. This is not a technical limitation. This is a legal limitation, in which the license you required for a piece of code, let's say like MATLAB, will let you run on a single instance of a machine. But if you need to run on 10 instances of a machine, if I use one license for all 10, then I'm in violation of those agreements. Companies like MATLAB, or the MathWorks, etc., have been working on dynamically acquiring and releasing licenses to get around this problem, and so we are looking at support for that. We are fine if you have a single-use license and you go ahead and only need to use that license for compilation or linking of the code. That's no problem, because you're only using it on one machine.